Okay, that looks good.
Good.
Okay. So yeah, so I'm very pleased to introduce the last of our three MIT faculty speakers. Bilge Yildiz is a professor of nuclear science and engineering and a professor of material science and engineering here at MIT and in the Center for Computational Science and Engineering. And her work focuses on science and technology at the intersection of essentially of materials development for energy conversion applications in a whole host of environments and a host of application areas, ranging from energy generation and fuel cells to oil exploration and beyond. One interesting thing about Bilge's work is that she has both experimental and computational work happening in her lab. She works on new in situ microscopy and spectroscopy methods, and on the computational side on multi-scale methods that really try to bridge the gaps of time scale, length scale between what people can typically simulate using atomistic methods and what you can actually measure and attain in the laboratory. So that's an enormously challenging problem in which Bilge has done a lot of really fascinating work. So we're really pleased that you could be with us today and give us a talk on electrochemo-mechanical field effects on electronic properties of oxides. Thank you.
Thank you so much, Joseph, for the introduction and for having me participate in this year's symposium. And the title is a mouthful, right? Electrochemo-mechanical field effects. And that will mean that I will share with you our work in driving different properties, different electronic properties by external fields that are mechanical strain and electric field. And I will put this in context of functional oxides. So oxides in various applications where charge transfer reactions are important, in particular in energy conversion, for example, oxide gas, oxide liquid interfaces, where electrochemical reactions take place, which are critical for enabling energy conversion, such as with fuel cells and electrolyzers, as well as in information storage and processing, where oxide-oxide and oxide-metal interfaces are important for charge transfer to enable devices which can combine memory and processor, such as in resistive switching, memristor chips, that can enable energy-efficient, brain-inspired computing. These are just few examples where functional oxides, and in particular, thin film oxide geometries make the device. Okay, so when we run into this geometry of very thin oxide films, there are additional external drivers that we ought to consider beyond the nominal composition of the oxide that we put into this application. And those are strain, in particular, strain introduced by lattice mismatch through the interface of the functional oxide with its substrate, as well as strong electric fields, because these systems run under applied voltages and across an oxide thin film, this can translate to very strong electric fields. And so what I will share with you is that both strain and electric fields, strong electric fields, can change the nature, can change the properties of the material on par with compositional engineering. So these are not very well studied external fields in these applications. The field cares more about compositional engineering. But when you put a given nominal composition into the device that is sustaining large amount of strain or large extents of electric field, the properties can significantly vary. And how can we understand and quantify the material properties under these external drivers is the goal that I want to share with you. Okay, so we will start with strain, in particular elastic strain, which we have studied in my group in the last decade, specifically in the context of ionic defects. So we're dealing with oxides in energy conversion, in information processing. Oxygen is part of the lattice, and oxygen defects, ionic oxygen defects, are very important for the charge transport and charge transfer reactions in these oxide devices. And with this very high level sketch, what I'm trying to show is that when you apply compressive versus tensile strain, in most reactions that involve oxygen, these reactions become more favorable because we are reducing, for example, the migration energy barrier. We are making oxygen defects more favorable. We are making oxygen absorption at the surface more favorable. And so it appears that as you change the energy landscape in the material by strain, the oxygen defects respond favorably to the elastic strain. And we have studied this in a number of different classes of oxide, binary oxides, ternary oxides such as perovskite oxides, as well as derivatives of these perovskite oxides. So short point again, that oxygen defects under elastic strains respond positively in terms of their formation, mobility, charge transfer ease when we expand the lattice. So how about the electronic defects? That's a topic that we have more recently started examining, okay? And I will start with strontium titanium oxide as a model system, which is really both a model system and a state-of-the-art perovskite for a number of these energy and information applications. And the question is, when this thin film strontium oxide is in the device, which sustains strain, what is the resulting change in the electronic conductivity? And there are a few previous studies that have attempted to look at this. And theoretically, the first prediction that we see is that under tensile strain, the effective mass of the electrons go down, which should increase the mobility and therefore the electronic conductivity. And a few years later, there comes this experimental paper, which actually shows the opposite, that when you tensile strain strontium titanate by 1%, exactly the same as the theoretical prediction, the resistance actually increases. So there is an apparent inconsistency between this previous theoretical and experimental work, which assumed only free electron dominance in strontium titanate that would give rise to electronic conductivity through a band-like model, and the interpretations assuming only that model appear to be inconsistent. So our goal in this work has been to assess whether we can couple to the stability of different types of electronic defects in this material. And we will see that indeed we can, and it becomes a way to reconcile this previous inconsistency in literature. So what do we mean by this? Different defect types, different electronic defect types in strontium titanate, and how strain could change their relative stability. So the two different electronic defects that we refer to here are the free electron and small polaron. So by free electron, we mean delocalized electrons in the conduction band, which have fast band-like mobility, versus small polaron, which is localized electron on the titanium cation, which forms a localized in-gap state and shows hopping mobility, which is slow. Okay? And by combining first principles calculations with thermodynamic analysis, we could produce a temperature stress or temperature strain map to identify the stability regimes of these two different types of electronic defects, which have different implications for electronic conductivity. And for such a problem, the appropriate potential to assess the system in is the Helmholtz free energy, which gives us the free variables as the temperature, the X and Y lattice parameters of the material, such as in strained oxide thin films, as well as the stress along the Z-axis that the film would relax. So using the Helmholtz free energy calculations for the two different systems where we stabilize the free electron and where we stabilize the small polaron, we can look at the difference of these free energies and calculate the self-trapping energy, that is indicating the relative stability of the small polaron or relative stability of the trapped electron energy. And the lower the self-trapping energy, the more negative it is, the more dominant that defect will be. And again, we rely in part on density functional theory calculations, but also on quasi-harmonic approximation calculations to introduce finite temperature effects, in particular coupling to the internal energy and vibrational entropies. And the codes that we use for these calculations are VASP, which is a very widely used first principles based tool, and PhonoP, which allows us to introduce the finite temperature effects. And we are looking at a temperature range from very low to 1000 Kelvin, as well as a strain range going from minus few to plus few percent biaxial strain, which means a little bit compressive to a little bit tensile. And this work, as well as the other examples that I will show in this talk, is performed primarily by Yanting Chi, who is a PhD student in my group, as well as by Mustafa Youssef, who has been a previous postdoc and PhD student in my group, and in collaboration with Professor Kristen van Vliet. All right, so what do we find in terms of the relative stability of these electrons versus free electrons versus small polarons as a function of temperature and strain? So here we can look at the self-trapping energy that I have defined on the previous slide, and the units are in milli-electron volt. And we can see the border between negative and positive energies as a function of temperature and as a function of strain, compressive and tensile strain. And those borders will be the borders between the dominance of the free electron and the dominance of the trapped small polaron. And so this gives us a phase diagram for the stability of these two different dominance of these two different types of electronic defects. And if we were to look at this problem only from the perspective of internal energy, we would get a different map where the border between the small polaron and free electron is slightly different. But more importantly, we miss this high temperature regime where free electron dominates again because the entropy contribution from free electrons is greater than trapped small polarons. So this is the more accurate map that we take. And it has implications such that, as I've already said, free electrons are more mobile than small polarons. So if in your device you desire faster electronic conduction, this would mean that you should choose substrates that give compressive strain, in-plane compressive strain to the strontium titanate. And how can we validate this? So I've already told you that there are experiments in literature that we could potentially use. And in particular, by looking at the temperature dependence of the electronic conductivity that is measured, we can determine the dominant electronic defect. Because if we are dealing with a small polaron that conducts via hopping, which is a thermally activated process, the conductivity as a function of inverse temperature should show a decrease with decreasing temperature. Whereas if the free electron that is dominant, this is not an activated process. In fact, with increasing temperature, there is further scattering. So we see either a flat or a very shallow slope in the conductivity as a function of temperature. So now if we examine the experimental literature that reported the conductivity in strontium titanate with different strains, we can observe these different regimes of slopes. So in compressive strain regime, so -3, -1%, the slope of conductivity versus temperature tells us that this behavior is metallic. And that strain regime is consistent with our prediction of free electron being the dominant electronic defect. And if we look at the tensile data, that is +1% tensile strontium titanate, the conductivity is thermally activated, and that is also consistent with our prediction of small polaron that should show this thermally activated conduction. So we were quite pleased to see the consistency between our first principles based thermodynamic calculation of different electronic defect stabilities and the experimental behavior of the conductivity that arises from the free electron and small polaron behavior. So having shown this, as I have indicated in the previous slide too, this stability map for the electronic defects gives us some guidance on the regimes of strain versus conductivity. And if the goal is to obtain more conducting films, compressive strain regime is the ideal regime. Whereas if the goal is more insulating starting point, such as in high KT electrics, then the tensile regime is the desirable regime to work with. Okay, so that's one example on how the elastic strain in such devices can give rise to drastically different electronic properties. So now let's move to the effects of electric field, very strong electric fields, which are present in thin film electronic devices such as memoristic resistive switches, high K dielectric films, ferroelectrics. And in each of these applications, there are indications already that electric fields can affect the stability, configurations, transport properties of charged point defects. And again, I will go back to oxygen defects in this case. And there will be two ways that these electric fields couple to the properties and stability of charged point defects. One is electrochemical, and I will indicate that in the thermodynamics. And the second is really the strength of the electric field that will give rise to polarization of charges associated with the point defect. And the fields that we are dealing with in such thin film devices are on the order of, can go to the order of 10 megavolts per centimeter. So these are indeed very large fields where electronic polarization in the material is reasonable to expect. But under those non-classical, non-linear conditions, how does the stability of point defects, such as oxygen vacancies, vary? How do their transport properties vary? This is not explored, far from being explored quantitatively in the field. And that's a problem that I was very motivated about to probe a few years ago, and still so. So then what did we do? We can look at the Gibbs free energy of the system again. So let's look at the thermodynamics again. And beyond the internal energy, entropy contribution, pressure volume term, you see terms related to the chemical potential of the species, of oxygen, of electrons. And then these last two terms, which are introduced when you apply voltage, when you apply a potential. So the electrochemical effect is this second to last term, which is pretty much potential times the charge of the defect, which changes the Gibbs free energy. And the last term, which is electric field times the dipole, times the polarization in the system, is what becomes dominant or what becomes important enough to consider when the electric field is high enough in polarizable systems. Classically, this is typically ignored, okay? But under such high field devices, we believe it's important to consider this. So if we then, let's say, calculate the formation energy of a defect that carries charge, for example, an oxygen vacancy that has trapped electrons. So now this is called a neutral oxygen vacancy, but still it has 2 electrons trapped in the site where oxygen doesn't exist. The formation energy, electric Gibbs energy of formation for this defect includes a term in the end that considers the difference between the polarization of the defective and the defect-free system. Okay, so the internal energy difference under constant displacement field, that has been addressed in the past before. What we are looking at is this polarization work that is under constant electric field. How does the polarization work affect the stability of different point defects that carry charge in the material? And so if this polarization difference between the defective and the perfect system is non-zero, then we should of course see an effect in the formation energy beyond just the electrochemical effect of potential on the charge. All right, so we have started examining this problem in simple binary oxides. What we plot here is the internal energy of formation and electric Gibbs free energy of formation for oxygen vacancies with trapped electrons as a function of electric field. So we contrast these two plots because by considering this polarization work, we can see that the two plots look very different, not only quantitatively, but also qualitatively. That if we do not consider the polarization work, it appears that this defect becomes less and less stable with increasing field. But when we do consider the polarization work, the sign of the formation energy becomes negative and the defect becomes more favorable under increasing electric field magnitudes. And this is because the net dipole introduced because of this defect in the system is positive. So as a function of field, the net dipole introduced via the oxygen vacancy is positive. So this term is positive, and therefore the Gibbs free energy of formation for this defect becomes more negative. And so this is telling us that such an important defect with a trapped charge that becomes color centers, that can give magnetism, that can influence the electronic properties, become more favored under electric field. And the source of the polarization in the system, even though these oxides in their bulk nominal are not polarizable, they are not polarizable oxides, but the source in this case becomes predominantly the defect itself. So if you look at the charge density distribution under zero field and under about 20 megavolt per centimeter, we can see from the charge density distribution that primarily the polarization is arising because of the trapped electrons at the oxygen vacancy site. And there's a small contribution from the surrounding sites as well, but quantitatively the dominant contribution is from the trapped electrons. All right, so we see this interesting polarization behavior, and we can observe from that work that the extent of polarization introduced in this non-polarizable bulk material, but polarized because of the defect, depends on the lattice constant of the material that we have examined. So going from magnesium to strontium to calcium to barium oxide, the net polarization increases, and that is positively correlated to the lattice parameter of the oxide. So that made us to hypothesize that a key source of polarizability is perhaps the available volume for the electrons to polarize into. And a second source that we think is important is the neighboring ion chemistry, in particular, its ability to uptake electrons that are being polarized around it. And we see evidence to this also from literature in ferroelectrics, where the ferroelectricity comes from lone pair electrons, where the polarization in polarizable materials depends on the electronegativity of the neighboring transition metal cation. Okay, so how can we resolve the lattice volume versus the electronegativity effect in the materials that we care about? And I'll go back to the strontium titanate, the perovskite system that is technologically more relevant than the simple binary oxides that we have started with. Okay, so one way that we can resolve this lattice constant or lattice volume effect is by applying strain in the strontium titanate system. And we can contrast strontium titanate to larger lattice parameter materials like barium titanate, which is a very high K dielectric material. And we can even artificially fix them to be at the same lattice parameter with very similar chemistry to see if we obtain the same polarizability. And we can contrast a class of oxide like titanates to zirconates and hafnates, which have distinctly different electronegativities compared to among each other. Okay, so let's look at the strain effect first. So now strain effect on the polarizability under electric field. So the mouthful electro-chemo-mechanical coupling is really embodied in this problem. We're looking at the electric polarization as a function of strain on the defect chemistry of the material. Okay, so that is again the polarization introduced with oxygen vacancy. And now by varying the lattice constant, for example, in strontium titanate, going from compressive to tensile strain, we can clearly see an increase in the net dipole, increase in the polarization. Similarly, by going from compressive to tensile in barium titanate, we see an increase in polarization. Contrasting unstrained strontium titanate to barium titanate, we see an increase in polarization in the latter, the larger lattice parameter counterpart. So there is clear evidence here that as we keep the chemistry of the material very consistent, so stick to titanates, and only play with the lattice volume, we can strongly modulate the dipole, we can strongly modulate the polarization, again of these charged, again of these trapped electrons in the charge defect. Much stronger polarization, which we can see visually also in the strontium titanate, which is versus the barium titanate, the latter. Much stronger polarization in the barium titanate compared to strontium titanate because the former has a larger lattice parameter. And how about the chemistry effect? That is the electronegativity or electron sharing ability of the B site, that is neighboring the polarizing electron. Now we are contrasting titanium with respect to zirconium and hafnium on the B site. And we can clearly see that the higher electronegativity system titanate can polarize much more strongly compared to the zirconate and hafnate. And if we plot the local dipole moment as a function of electronegativity, we can see that relation, the positive relation, very clearly. With the hafnate and zirconate, we have small polarization and much stronger with the titanate system. And so in summary, we're finding that the lattice volume that you make available for polarization, as well as the neighboring ion electronegativity, are comparably important in giving rise to polarization of charge defects under electric fields. And this is really a problem where the coupling of electricity or electrical properties with chemical properties and mechanical properties is prominent. So that's why we're referring to this as electro-chemo-mechanically coupled relationship that defines the point defect polarization as a function of strain and transition metal electronegativity are important for us to see, because this way we understand the material properties under functional conditions more accurately. And it also gives us ideas for how to design the geometry and the chemistry of the oxide depending on the desirable electronic defect. For example, if you want stronger polarization, obviously going to larger lattice volumes and higher electronegativity chemistries is desirable. Good, so I will end here by repeating that the fields that couple electrochemomechanics, which are not nearly as much studied as traditional composition engineering of the oxide, are in fact important drivers of electronic properties on par with the engineering of the composition, for us to be able to understand the device properties and ultimately to engineer the device properties. As I have shown to you under strain fields, we can change the stability among electronic defects, which have drastically different implications for electronic conductivity. And we can change the stability of different types of ionic defects and their electronic polarization under electric fields, which have implications for energy conversion and electronic devices such as memory step systems that I have motivated us to start with. So I will end here by again thanking my PhD student Yenting Chi. He's right here. He has been doing all the work that I have shared with you in collaboration with Dr. Mustafa Youssef and Professor Kristen Van Vliet. And thanks a lot for your attention.
Thank you, Bilge. So, okay, thanks for the great talk. We have time for a few questions from the audience. I have one question to start it off from someone sort of not in the field, but at the end when you sort of talked about using this kind of engineering, something comparable to engineering composition, I guess how far are we from being able to start to do kind of automated design and discovery of electro-chemo-mechanical properties? I mean, it sounds like the just understanding them is a much earlier stage, but what are kind of what's the roadmap there?
We are thinking about that. So you're right. The understanding is in its early stage. And for example, the plot here was as a function of just biaxial strain, the simplest type of strain we can introduce in a device. But is this the most optimal strain for us to very strongly stabilize one type of defect versus the other? So that would need more, let's say, coupling, not really like a hypothesis-driven research, but coupling to data and machine learning, for example, to inverse design the optimal strain tensor. Strain tensor could be any complex direction that would give the most ideal outcome, but we don't know that yet, right? So we're in this process of understanding the coupling of strain and electric fields to these outcomes, but we are considering next, especially in the context of strain, to couple the DFT calculations with machine learning algorithms to give us the best strain tensors with the most optimal ionic or electronic outcomes.
Yeah, okay, cool. That sounds really interesting. Any other questions from the audience? Okay, well, if not, I think we can thank Bilge again and thank all the speakers of the past block.
Thank you.
For this series of interesting talks.